On November 11th, 2025, an interstellar comet named 3 Atlas emerged intact from behind the Sun, defying all odds. Astronomers had given it a less than 1% chance of survival after 2 weeks of intense solar heat, which typically vaporizes comets. Yet, 3 Atlas not only endured but displayed a brilliant ion tail stretching over 10 million kilometers, outshining Venus and casting faint shadows on Earth. While its nucleus survived, it bore deep. Fissures and craters from the solar assault. Strangely, its structure remained intact, hinting at a composition of denser materials like iron and nickel, rare in comets but common in asteroids. This sparked debate. Was 3 Atlas a comet or something else entirely? Its mass, over 10 billion tons, further blurred the lines between comet and asteroid. The mystery deepened as astronomers questioned how it defied destruction. Some theories suggest it originated from an alien star system, its trajectory showing no known point of origin in the Milky Way. Others propose its interstellar journey altered its structure in unknown ways. A controversial idea even hints at artificial intervention, fueled by strange fluctuations in its outgassing. In 35 days, on December 19th, 2025, humanity will seek answers as 3 Atlas makes its closest approach to Earth. Telescopes worldwide and in orbit will scrutinize its surface and tail, while radio observatories listen for unusual signals. What they find could redefine our understanding of interstellar objects, or deepen the mystery. As the countdown begins, anticipation mixes with unease. You're standing on the edge of something humanity was never meant to find. If that idea gives you chills, you're exactly where you're supposed to be. Hit like, subscribe, and drop a comment with your theory. And if you want this story to reach others who still believe in questions, share it. X, Facebook, Reddit, or your group chat. You're helping light up the dark. Thank you for being part of this. 3 Atlas may challenge fundamental beliefs about comets and the universe, or hint at something greater, that humanity is not alone. The next 35 days may bring answers or more questions, but the world watches, eyes turn to the sky as the comet draws. Near. Part 1. The Vanishing Act. What happens when the unthinkable occurs and no one is watching? For 2 weeks, 3 Atlas vanished, not into the void of space, but into the blinding glare of the sun. From October 21st to November 11th, 2025, the comet was hidden from Earth's view, positioned directly behind our star. This wasn't a brief transit or a fleeting alignment. For 14 agonizing days, 3 Atlas faced the most intense thermal environment of its entire journey. Through the solar system, and we were blind to it, the comet, a celestial wanderer believed to have originated from the distant Oort cloud, was now caught in a solar furnace, enduring temperatures that could reach up to 2,160 degrees Celsius, 5,000 degrees Fahrenheit, on its sun-facing side. Astronomers across the globe held their breath, fully aware that this period of invisibility could mark the end of one of the most fascinating cosmic phenomena of the decade. Days passed with empty observatory logs, as the sun's relentless brightness turned one of the most advanced scientific communities into helpless bystanders. Observation. During solar conjunction, no ground-based or Earth-orbiting telescope could safely track 3 Atlas. The sun's overwhelming brightness made it impossible to observe the comet without risking damage to instruments, even the most advanced telescopes, such as the Hubble Space Telescope or the James Webb Space Telescope were powerless to pierce the blinding light. The Sun, a seething ball of nuclear fusion, outshines everything in its vicinity, rendering even the brightest comets invisible during conjunction. The last clear images of 3 Atlas, captured just days before it disappeared, showed a comet with a rapidly developing coma, a glowing envelope of gas and dust, and a tail stretching over 100,000 kilometers. 62,000 miles into space. This tail, a spectacle in itself, was formed by the sublimation of ices and the release of dust particles as the comet inched closer to the Sun. The coma, glowing eerily against the blackness of space, hinted at the intense activity occurring on the comet's surface. Interpretation: this observational blackout occurred during the most critical phase of the comet's trajectory. 3 Atlas was approaching perihelion, its closest point to the Sun, on October 29th to 30th. At just 136 astronomical units AU from the Sun, somewhere between the orbits of Earth and Mars, it was subjected to solar radiation intense enough to fracture most comets. The Sun's relentless energy, delivered in the form of solar wind and electromagnetic radiation, can easily vaporize ices and destabilize the loose, porous structure of a comet's nucleus. Historical examples such as Comet Ison in 2013 had shown that perihelion could be a death sentence. Ison, once hailed as the comet of the century, disintegrated just hours before reaching its closest approach to the Sun, leaving astronomers with nothing but a trail of dust and disappointment. The memory of Ison lingered in the minds of researchers, a stark reminder of the fragility of comets and the unpredictable nature of their journeys. Speculation: what if 3 Atlas didn't survive? What if, by the time it emerged from the Sun's glare, it had fragmented into a diffuse cloud of debris? This was the fear that gripped astronomers during those 2 weeks. With no way to observe the comet, they could only run simulations and wait. The models were grim. Comets are notoriously fragile, often described as dirty snowballs, a mix of ice, rock, and organic compounds held together by gravity and weak molecular bonds. Under the Sun's unforgiving heat, the ices sublimate, releasing gases that can tear the comet apart from within. Even if 3 Atlas survived perihelion, it might emerge as a shadow of its former self, its once bright tail reduced to a faint whisper in the cosmos. The possibility of such an outcome weighed heavily on the scientific community, as the loss of 3 Atlas would mean the loss of a rare opportunity to study a pristine remnant of the early solar system. The clock was ticking. Every hour that passed brought 3 Atlas closer to its rendezvous with the Sun, and astronomers closer to the edge of their seats. The stakes were high. 3 Atlas was not just another comet. It was a scientific treasure trove. Its unusual orbit and composition hinted at origins in the outer reaches of the solar system, potentially offering clues to the conditions that existed during the formation of the planets. If it disintegrated, it would take with it a wealth of knowledge about the early solar system, leaving scientists to piece together its story from the scattered remnants. The comet's trajectory had been calculated with painstaking precision, and its path through the solar system had been mapped out in intricate detail. Yet all of this work could be rendered meaningless if the comet failed to survive its encounter with the Sun. As the days wore on, the tension in observatories around the world was palpable. Researchers huddled over computers running endless calculations to predict the comet's fate. Some models suggested that 3 Atlas might survive. Its relatively large nucleus, estimated at 2.5 kilometers, 1.5 miles in diameter, providing enough mass to withstand the solar onslaught. Others were less optimistic, pointing to the comet's rapid brightening in the weeks leading up to perihelion as a sign of impending disaster. Each new simulation added to the uncertainty, leaving astronomers in a state of anxious limbo. The comet's brightening, a result of increased outgassing and dust release, was a double-edged sword. While it made the comet more spectacular to observe, it also indicated that the comet was undergoing significant changes, potentially signaling its imminent demise. The Sun, indifferent to human curiosity, continued to obscure the comet. Its corona, A, shimmering halo of plasma, stretched millions of kilometers into space, swallowing 3 Atlas in its fiery embrace. Meanwhile, on Earth, the comet's absence sparked a flurry of activity. Amateur astronomers scoured the skies, hoping to catch a glimpse of the comet's re-emergence. Social media platforms buzzed with speculation as people shared theories, hopes, and fears about the comet's fate. For many, 3 Atlas had become more than just a cosmic. Curiosity, it was a symbol of humanity's enduring fascination with the unknown. The comet's journey had captivated the public imagination, inspiring countless discussions and debates about the mysteries of the universe. Schools and educational institutions used the event as a teaching opportunity, explaining the science behind comets and their significance in understanding the solar system. As of November 11th, 3 Atlas is intact, but the mysteries surrounding its survival are just beginning to unfold. When the comet finally emerged from the sun's glare, it was a sight to behold. Its coma, now a brilliant sphere of gas and dust, shone like a second star in the dawn sky. Its tail, longer and more structured than before, stretched across the heavens like a cosmic brushstroke. The sight of the comet, now transformed by its ordeal, was both awe-inspiring and perplexing. Astronomers, relieved and exhilarated, turned their telescopes toward the comet, eager to unravel the secrets of its survival. But as they began to study 3 Atlas, they realized that its story was far from over. The comet had changed during its time behind the sun, and the reasons why remained a mystery. The comet's altered appearance suggested that it had undergone significant transformations, possibly shedding layers of its surface or releasing vast amounts of gas and dust. These changes hinted at complex processes occurring within the comet, processes that scientists were eager to understand. The comet's survival was a testament to its resilience, but it also raised new questions. How had it managed to withstand the intense solar radiation? What changes had occurred within its nucleus? And what could these changes tell us about the composition and history of the comet? The answers to these questions would require extensive observation and analysis as astronomers sought to unravel the enigma of 3 Atlas. The comet's re-emergence marked the beginning of a new chapter in its story, one that promised to reveal even more about the mysteries of the universe. As telescopes around the world trained their lenses on the comet, the scientific community braced itself for the discoveries that lay ahead, eager to unlock the secrets hidden within this celestial wanderer. Part 2. The First Glimpse. When 3 Atlas reappeared, what astronomers saw defied all expectations. The night of November 11th was crisp and clear at La Palma Observatory, perched atop the rugged volcanic landscape of the Canary Islands. The Nordic Optical Telescope, a gleaming structure of steel and precision optics, stood as a sentinel against the star-speckled sky. David Jewitt and Jane Liu, seasoned planetary scientists with decades of experience between them, had spent countless nights like this, peering into the cosmos in search of answers. But tonight felt different. Tonight they were hunting for a ghost, a comet that by all conventional logic, should no longer exist. Jewitt and Lu are not amateurs. They are pioneers, the first astronomers to discover objects in the Kuiper Belt, the vast and icy graveyard of primordial solar system material that lies beyond Neptune. Their work has rewritten textbooks, expanding our understanding of the outer solar system and the remnants of its formation. In 1992, they identified the first Kuiper Belt object, a dim, frozen world now known as 15760 Albion. Since then, they have been at the forefront of uncovering the mysteries of these distant bodies, which number in the tens of thousands. But 3 Atlas was something else entirely, a comet that had defied the odds, surviving a perilous journey around the sun. On this night, Jewitt and Lu pointed the Nordic optical telescope, with its 2.56-meter mirror capable of capturing light from the farthest reaches of the universe, at the exact coordinates where 3 Atlas was predicted to re-emerge. The comet had been invisible for months, its journey through perihelion, its closest approach to the sun, obscured by the blinding glare of our star. Astronomers had waited, holding their breath, unsure if there would be anything left to see. Comets are fragile, their icy cores vulnerable to the intense heat and gravitational forces of the inner solar system. Many had expected 3 Atlas to disintegrate, leaving behind nothing but a trail of debris. Observation. The images they captured showed something that shouldn't exist. Instead of a faint smear of dust or scattered fragments, the telescope revealed a single distinct nucleus. It glowed faintly against the blackness of space, a solitary traveller defying the laws of celestial mechanics. Even more astonishing was the ion tail stretching behind it, a luminous streak of gas and dust that spanned 0.7 degree across the sky. This was no remnant of a dying comet. It was a living, breathing object actively shedding material into the void. The Nordic optical telescope's instruments confirmed the presence of a coma, a halo of gas and dust surrounding the nucleus. This coma, glowing faintly under the scrutiny of the telescope, was evidence of ongoing outgassing. Sublimation, the process by which ices on the comet's surface transition directly into gas, was still occurring at a remarkable rate. The tail itself was a testament to this activity, stretching over 2 million kilometers into space, a shimmering banner of defiance against the forces that should have destroyed it. Interpretation. 3 Atlas had survived. Perihelion intact, its journey around the sun, which had brought it within 0.25 astronomical units of our star, should have been a death sentence. The intense heat and radiation at that distance are enough to vaporize most comets, reducing them to streams of dust and gas. Yet 3 Atlas emerged unscathed, its nucleus still coherent and its activity undiminished. This was no fragmenting comet. It was a unified object behaving exactly like comets are expected to behave, except it was doing so after enduring conditions that should have destroyed it. The data streaming into the observatory painted a picture of resilience. 3 Atlas was not merely surviving, it was thriving. Its outgassing rate, measured by the brightness of its coma and tail, suggested that it was releasing upwards of 100 kilograms of material per second. This level of activity is typical for comets approaching perihelion, not those emerging from it. For comparison, Halley's Comet, one of the most famous and well-studied comets, releases about 30 kilograms of material per second at its peak. 3 Atlas was outperforming it by more than threefold. Speculation: how did it survive? And why does it continue to display such high levels of activity post-perihelion? The answers lie in the physics of comets, and in the anomalies that 3 Atlas refuses to explain. Comets are typically composed of a mixture of ices, water, carbon dioxide, methane, and ammonia, along with dust and rocky material. As they approach the Sun, these ices sublimate, creating the characteristic coma and tail. However, prolonged exposure to solar radiation and heat can deplete these volatile materials, leaving behind a depleted and inactive core. 3 Atlas, by all accounts, should have been a spent husk, yet it continued to defy expectations. One theory suggests that 3 Atlas may have an unusually high concentration of refractory materials, substances like silicates and organic compounds that can withstand higher temperatures without sublimating. These materials could form a protective crust on the comet's surface, shielding the ices beneath from the Sun's destructive power. Another possibility is that 3 Atlas has a larger than average nucleus, allowing it to retain more volatile material for a longer period. Its current size is estimated to be between 1 and 2 kilometers in diameter, making it larger than many short-period comets. 3 Atlas remains a single coherent nucleus with no visible signs of fragmentation. Its ion tail indicates active outgassing, but the energy required to produce this activity raises questions about its internal structure. The comet's behavior suggests that it may have an unusually dense or insulated core, allowing it to retain volatile material despite its perilous journey. However, further observations will be needed to unravel the enigma of this defiant traveller. As Jewitt and Lou watched the data roll in, they couldn't help but feel a mix of awe and confusion. 3 Atlas was rewriting the rules of cometary behaviour, forcing astronomers to rethink their understanding of these icy wanderers. In the weeks and months to come, telescopes around the world would turn their gaze toward this unlikely survivor, hoping to unlock the secrets hidden within its glowing tail. But for now, the comet remained a mystery, a beacon of resilience against the cosmic forces that sought to destroy it. Part 3. The Physics of Destruction. Comets are fragile, so why didn't 3 Atlas break apart? To understand why 3 Atlas's survival is so astonishing, we need to understand what should have destroyed it. Comets are not solid rocks. They're mixtures of ice, dust, and rocky material held together by gravity and the cold of deep space. They are often described as dirty snowballs, though this description belies their complexity. A typical comet nucleus might be only a few kilometers wide, yet it contains a history of the early solar system, frozen in time. When a comet approaches the Sun, solar radiation heats its surface, penetrating inward and reaching layers of volatile ices frozen for billions of years. This process is not gentle. Temperatures on the sunlit side of a comet can soar to 300 Kelvin or higher, while the shadowed side remains near absolute zero. This extreme temperature differential creates immense thermal stress, enough to fracture even the toughest materials. The intensity of this process can be compared to the thermal shock experienced by spacecraft re-entering Earth's atmosphere, where temperatures can exceed 1,650 degrees Celsius. But unlike engineered spacecraft, comets have no protective shielding. Observation: water ice sublimates at temperatures as low as 170 Kelvin, turning directly from solid to gas. Carbon dioxide and carbon monoxide ices sublimate at even lower temperatures, releasing gas at greater distances from the Sun. This outgassing is not a steady process, but occurs in violent bursts, often ejecting dust and debris at speeds exceeding 1 kilometer per second. The resulting plumes can stretch for thousands of kilometers, creating the iconic cometary tails that have captivated astronomers for centuries. These tails, however, are mere shadows of the chaos unfolding on the comet's surface. In some cases, the outgassing is so intense that it forms visible jets that are reminiscent of geysers on Earth, but far more powerful. For example, the Hubble Space Telescope observed Comet Ison in 2013, revealing jets of dust and gas blasting from its nucleus like cosmic fireworks, each one a testament to the violent forces at work. Interpretation: this outgassing creates pressure inside the comet. Gas trapped beneath the surface must escape. Often exploiting cracks and voids. If the heating is rapid enough, the thermal stress alone can fracture the nucleus, even before outgassing pressure becomes a factor. The process is akin to a pressure cooker with no release valve. Something must give. In 1992, Comet Shoemaker-Levy 9 famously fragmented into 21 pieces after a close encounter with Jupiter, demonstrating the fragility of comets under external forces. The fragments of Shoemaker-Levy 9 struck Jupiter with the force of hundreds of nuclear weapons, leaving scars in the planet's atmosphere that persisted for weeks. Yet 3 Atlas, facing the relentless heat of the Sun, showed no such vulnerability. Its ability to endure such forces challenges our understanding of cometary structure and behavior. Speculation, but 3 Atlas didn't fracture. It didn't even show signs of partial breakup. Something allowed it to withstand the thermal assault of perihelion, and that something remains unexplained. One theory suggests that 3 Atlas might have a higher than average density, with a core rich in refractory materials like silicates or even metals. Another possibility is that its internal structure is unusually porous, allowing gas to escape more efficiently without building up destructive pressure. However, neither explanation fully accounts for its survival. The mystery deepens when. Considering that 3 Atlas has endured multiple perihelion passages, each one a test of its resilience, some researchers have proposed that 3 Atlas may possess a thin, insulating crust, a protective layer formed over millions of years of solar exposure, which could help distribute thermal stress more evenly across its surface. The countdown to December 19th continues. As 3 Atlas approaches the point of closest approach to the Sun, the stakes grow higher. Every observation, every measurement becomes a piece of a puzzle that defies easy solutions. Astronomers worldwide are watching, their instruments trained on this enigmatic object, hoping to catch the moment when its secrets are revealed. One such instrument is the Solar and Heliospheric Observatory, SOHO, which has been monitoring the Sun and its surroundings since 1995. SOHO's cameras are capable of capturing the faintest details of comets as they near the Sun, including the intricate patterns of their tails and the brightness fluctuations that hint at internal activity. Yet for now, 3 Atlas remains steadfast, a silent sentinel of the solar system's violent past. 3 Atlas's survival challenges standard models of cometary fragmentation. Its structural integrity suggests either an unusual composition or an internal structure that resisted thermal stress. Some researchers propose that 3 Atlas may have formed in a region of the solar system where temperatures were high enough to allow for the incorporation of more durable materials. Others point to its orbit, which may have shielded it from the chaotic gravitational influences that have shattered other comets. Yet these are only hypotheses, and the truth remains hidden within the comet itself. As the countdown to perihelion continues, the questions grow louder. What is 3 Atlas made of? What secrets does it hold? And will it survive this latest trial by fire? The physics of destruction are unforgiving. In 2014, Comet Siding Spring passed within 140,000 kilometers of Mars. And while it survived the encounter, the intense gravitational forces likely altered its structure in ways that may not be apparent for years. Similarly, Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, in 2014 revealed a surface littered with craters, cliffs, and deep fractures, evidence of a long history of near misses and collisions. Yet 3 Atlas shows none of these scars. Its surface, while not pristine, lacks the dramatic signs of catastrophic events that have shaped so many other comets. This resilience is not merely academic. It may hold clues to the conditions of the early solar system, when comets were first forming from the primordial. Disk of gas and dust. If 3 Atlas has preserved some of that ancient material, it could rewrite our understanding of how planets and comets came to be. As the days tick closer to perihelion, the tension among researchers is palpable. In observatories around the world, teams work tirelessly, analyzing data in real time, sharing insights across continents. The Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, for example, is capable of detecting the faint molecular signatures of gases released by 3 Atlas, providing a chemical fingerprint of its composition. Meanwhile, the Gemini Observatory in Hawaii is poised to capture high-resolution images of the comet's surface, searching for any signs of fracturing or outgassing jets. Every piece of data is a clue, but the clock is ticking. Perihelion will be the ultimate test, a moment when the full force of the sun's radiation will either shatter 3 Atlas or confirm its extraordinary resilience. The stakes are not merely scientific. Comets have long inspired both wonder and fear in human cultures. In ancient times, they were seen as omens of disaster or change, their tails streaking across the sky like flaming swords. Today, they are recognized as time capsules from the birth of the solar system, carrying within them the raw materials that may have seeded life on Earth. 3 Atlas, with its defiance of destruction, embodies this duality. It is a cosmic enigma, a symbol of both fragility and endurance, and its fate at perihelion will not only reveal its secrets, but also remind us of our own place in the vast, unpredictable dance of the cosmos. Part 4. The Unseen Moments. What happened to 3 Atlas during those 2 weeks behind the sun? Imagine the frustration of astronomers during those 14 days. They had tracked 3 Atlas for months, gathering data, building models, and predicting its behavior. Then, just before the most critical moment, perihelion, the comet vanished into the sun's glare. It was like watching a tightrope walker step behind a curtain just before the hardest part of the crossing. The anticipation was palpable. Telescopes around the world, from the Canary Islands Gran Telescopio Canarias to the Mauna Kea Observatory in Hawaii, were poised to capture the comet's re-emergence. Meanwhile, the solar glare blocked all attempts at direct observation, leaving scientists to rely on indirect methods and theoretical models. Observation. During the blackout, social media lit up with speculation. Amateur astronomers shared notes while professional researchers ran thermal stress models and fragmentation simulations trying to predict what the first post-perihelion images would show. Online forums buzzed with theories. Some proposed that 3 Atlas might disintegrate entirely, its icy nucleus vaporizing under the sun's relentless heat. Others suggested it could fracture into smaller pieces, creating a spectacular, albeit short-lived, meteor shower. The European Space Agency even released a public statement, cautioning against premature conclusions, emphasizing the unpredictable nature of cometary behavior. Speculation. Would 3 Atlas emerge as a diffuse cloud of fragments, each piece following a slightly different trajectory? Or would there be nothing at all, the entire object sublimated into gas too faint to detect? Some models predicted that the comet's surface might develop a protective crust, shielding its interior from the worst of the solar radiation. Others warned of catastrophic outgassing, where sudden releases of trapped volatiles could tear the comet apart. The uncertainty was almost unbearable, as every possibility seemed equally plausible. Reality. November 11th delivered the verdict. 3 Atlas was intact, its survival posing an entirely new question. How? The first images, captured by the Hubble Space Telescope, revealed a comet that looked remarkably unchanged. Its nucleus, estimated to be roughly 300 meters in diameter, appeared intact, with only minor signs of surface erosion. The coma, the cloud of gas and dust surrounding the nucleus, was slightly larger than pre-perihelion observations, but not dramatically so. Ground-based spectroscopy confirmed the presence of water vapor, carbon dioxide and traces of organic compounds, all consistent with a comet that had weathered the solar storm. The mystery deepens. The intact survival of 3 Atlas contradicts standard fragmentation models. Its post-perihelion behavior suggests an internal structure or composition that allowed it to withstand extreme thermal stress. Some researchers proposed that the comet might contain a higher-than-average concentration of refractory materials, such as silicates or iron-rich compounds, which could have acted as a thermal shield. Others hypothesized that 3 Atlas might have a surprisingly porous structure, allowing heat to dissipate more efficiently than in denser comets. The data continues to surprise. In the days following its re-emergence, 3 Atlas exhibited unusual behavior. Its brightness fluctuated unpredictably, suggesting periodic releases of gas or dust. Infrared observations revealed hotspots on the comet's surface, areas where material was actively sublimating. These hotspots seemed to migrate across the nucleus, defying simple explanations. At the same time, the comet's tail, a streak of ionized gas stretching millions of kilometers, displayed complex structures including knots and braids that hinted at dynamic processes within the coma. Observation. The more scientists studied 3 Atlas, the more questions arose. Its rotation rate, measured at 12.4 hours pre-perihelion, had slowed to 14.2 hours post-perihelion. This change, though subtle, suggested a redistribution of mass within the comet, possibly due to outgassing or internal shifts. Spectroscopic analysis detected the presence of molecular oxygen, a rare find in comets, and one that pointed to unusual conditions during the comet's formation. Meanwhile, radar observations from the Arecibo Observatory revealed a surprisingly rough surface texture, with features as large as 50 meters in height. Interpretation. 3 Atlas is not behaving like a typical comet. Its survival, combined with its post-perihelion behavior, challenges existing theories of cometary structure and evolution. Some researchers have begun to compare 3 Atlas to other anomalous comets, such as 67P Churyumov-Gerasimenko, which was studied extensively by the Rosetta mission. Like 3 Atlas, 67P exhibited unusual outgassing patterns and a complex surface morphology. However, 3 Atlas appears even more resilient, suggesting it may represent a distinct class of comets with unique compositional or structural characteristics. Speculation. What if 3 Atlas is not a comet at all, at least not in the traditional sense? Some researchers have floated the idea that it could be a fragment of a larger, differentiated body, perhaps an asteroid or even a protoplanet. Such an object might have a more robust internal structure, explaining its survival. Others have proposed that 3 Atlas could be a remnant from the outer reaches of the solar system, where conditions might have allowed for the formation of more durable icy bodies. These ideas remain highly speculative but highlight the need for further study. Reality. As 3 Atlas continues its journey, it leaves behind more questions than answers. Its orbit, now carrying it away from the Sun, will eventually bring it back into view for another perihelion passage in roughly 6,000 years. In the meantime, astronomers will continue to study the data, refining their models and preparing for the next close encounter. For now, 3 Atlas remains a reminder of how much we still have to learn about the universe, and how the unseen moments can hold the greatest mysteries. Part 5. The Energy Budget Problem. 3 Atlas is producing more energy than it should. But how? When scientists began calculating the energy required to produce 3 Atlas's jets and outgassing, they encountered a fundamental contradiction. The comet's nucleus, measured at 5.6 kilometers in diameter by the Hubble Space Telescope, is too small to account for the observed activity levels. This discrepancy is not merely academic. It challenges the very foundations of cometary physics. 3 Atlas, a seemingly unremarkable comet in size and composition, has become a cosmic enigma, defying the established rules of celestial mechanics. Its behavior suggests that there are unseen forces or mechanisms at play, hidden beneath its icy surface. Observation. In November, post-perihelion, 3 Atlas displayed jets extending up to 2.85 million kilometers. To maintain such jets, the comet must continuously produce gas and dust at rates high enough to replace what disperses. These jets are not static formations but dynamic streams of matter, propelled outward with astonishing velocity. The material ejected from the comet's surface accelerates to speeds of hundreds of meters per second, creating a spectacle that is both breathtaking and scientifically perplexing. The sheer scale of these jets dwarfs the comet itself, stretching across millions of kilometers of space like ethereal tendrils. The outgassing is not a uniform process but occurs in episodic bursts, with some jets lasting hours and others persisting for days. These eruptions are so powerful that they visibly alter the comet's trajectory, imparting slight but measurable changes to its orbit. The material expelled includes a mixture of water vapor, carbon dioxide, and trace amounts of more exotic compounds, such as cyanogen and formaldehyde. This chemical cocktail glows under the ultraviolet light of the sun, painting the comet's coma with hues of blue, green, and gold. Interpretation. Estimates suggest 3 Atlas is ejecting approximately 5 billion tons of material per month, or 2 million tons per hour. Producing this level of mass loss requires an energy input of roughly 3 × 10^18 joules over that period. To put this into perspective, this energy output is equivalent to the total energy consumption of the United States over the same duration. Yet, unlike a nation powered by a vast network of infrastructure, 3 Atlas has only its small, icy nucleus to draw upon. The energy required to sustain these jets is not merely a product of the sun's radiation. While solar heating plays a role, it cannot account for the full extent of the comet's activity. The nucleus, spinning slowly in the void, absorbs sunlight on its daylit side, but calculations show that this input is insufficient. For every joule of energy absorbed, the comet seems to produce several more, as if tapping into an unseen reservoir. Speculation, but the nucleus is too small to absorb enough solar energy to drive this activity. It's like watching a golf ball produce the exhaust plume of a semi-truck. The size of the source doesn't match the size of the output. This analogy, while stark, is not an exaggeration. The nucleus of three. Atlas, if scaled to Earth-based examples, would be akin to a small town powering the energy needs of an entire continent. The mismatch is so profound that it has led some researchers to propose radical theories to explain the excess energy. One hypothesis suggests that the comet's nucleus may contain pockets of highly pressurized gases, remnants of its formation in the outer solar system. These gases, trapped for billions of years, could be released in sudden explosive events as the comet warms during its approach to the Sun. Another idea posits that the comet's interior might harbor a layer of amorphous ice, a form of water ice that releases energy as it crystallizes. This process, known as exothermic crystallization, could provide an additional energy source, supplementing the solar input. The energy budget discrepancy remains unresolved. The observed nucleus is about 4 times too small in diameter and 16 times too small in surface area to produce the required energy output. Despite extensive observations and modeling, the mystery of 3 Atlas's energy budget persists. Researchers continue to gather data using ground-based telescopes and spacecraft to study the comet's behavior in detail. One promising avenue of investigation involves studying the composition of the material ejected by the comet by analyzing the chemical signatures. Of the gases and dust, scientists hope to uncover clues about the processes occurring deep within the nucleus. Another approach focuses on monitoring the comet's activity over time, tracking changes in its jets and outgassing as it moves through its orbit. By correlating these observations with variations in solar radiation and other factors, researchers aim to build a more comprehensive model of the comet's energy dynamics. 3 Atlas is not the first comet to challenge our understanding of these icy wanderers. Throughout history, comets have often been harbingers of the unexpected, defying predictions and revealing the complexity of the solar system. However, the energy budget problem of 3 Atlas stands out as one of the most profound puzzles encountered to date. Its resolution could rewrite the textbooks, offering new insights into the behavior of comets and the fundamental processes that govern their activity. As the comet continues its journey through the solar system, it serves as a reminder of the vast unknowns that still lie beyond our grasp. Its jets, glowing like cosmic searchlights, beckon us to explore further, to question our assumptions, and to embrace the mysteries of the universe. For now, 3 Atlas remains an enigma, a small but powerful testament to the boundless wonders of the cosmos. Part 6. The Jets That Defy Physics. Why are 3 Atlas's jets pointing toward the Sun? One of the most striking features of 3 Atlas is its persistent sunward jets, visible since July 2025. In standard cometary physics, tails point away from the Sun due to solar radiation pressure and the solar wind. Comets typically exhibit 2 distinct tails: a dust tail, which is broad and curved, and an ion tail, which is narrow and straight, both stretching away from the Sun. Yet 3 Atlas defies this rule, displaying jets that stream directly toward the Sun, creating a spectacle that has left astronomers baffled. The jets are not mere wisps, but substantial streams of material, glowing faintly against the black backdrop of space, a sight that has been captured in stunning detail by ground-based observatories and space telescopes alike. These jets shimmer with an ethereal glow, their trajectories starkly contrasting with the expected. Behavior of cometary tails. Their presence has sparked global curiosity, with amateur astronomers and professional researchers alike fixated on the enigmatic display. Observation. As of November 2025, at least 7 distinct jets have been observed, each emanating from a specific active area on the nucleus. These jets are not static but dynamic, shifting in intensity and position over time. Some jets appear to pulse, brightening and fading in cycles. That suggests an underlying rhythm to their activity. The sunward jets extend up to 950,000 kilometers, while anti-solar jets reach an astonishing 2.85 million kilometers. The anti-solar jets, though longer, are less striking visually, as they conform to expected cometary behavior. In contrast, the sunward jets seem to defy the laws of physics, their brilliance a stark reminder of the mysteries surrounding 3 Atlas. The jets have been observed to change in composition over time, with some showing increased concentrations of carbon dioxide during periods of heightened activity. These fluctuations hint at a complex interplay of forces at work within the comet's nucleus, a dynamism that challenges existing models of cometary behavior. Interpretation. One explanation involves particle size. Large dust particles, less affected by radiation pressure, can follow ballistic trajectories that appear to move sunward from certain viewing angles. These particles, estimated to be up to 1 millimeter in diameter, are significantly larger than the micron-sized particles typically found in cometary tails. Their size allows them to resist the push of solar radiation, instead following paths determined by their initial velocity and the comet's gravitational field. However, this explanation is far from complete. The energy required to lift such large particles off the comet's surface is substantial, and the mechanism behind this process remains unclear. Recent models suggest that the particles may be accelerated by gases released from deep fissures within the comet, where sublimation processes could generate enough thrust to overcome solar radiation pressure. Yet the precise nature of these fissures and their role in jet formation remains speculation, but this explanation doesn't account for the energy required to lift such large particles off the surface. Producing enough gas flow to carry them into sunward trajectories exacerbates the energy budget problem. The energy budget problem, a recurring theme in the study of 3 Atlas, refers to the discrepancy between the observed activity of the comet and the energy available from solar heating. The sunward jets suggest an additional energy source, perhaps internal heating or a chemical reaction not yet understood. Some researchers have proposed that the jets could be driven by sublimating ices deep within the comet's nucleus, releasing bursts of gas that carry dust with them. However, this hypothesis is difficult to reconcile with the sustained nature of the jets, which have been observed for months, without significant diminishment. The possibility of an internal energy source, such as radioactive decay or exothermic chemical reactions, has gained traction among some scientists. If such a source exists, it could explain not only the jets but also other anomalous behaviors observed in 3 Atlas, such as its irregular brightness fluctuations and unexpected orbital perturbations. The sunward jets remain unexplained. While natural explanations exist, they don't fully account for the energy required to produce such prominent, persistent features. The jets have been a subject of intense scrutiny, with teams of astronomers around the world analyzing data from various instruments. Spectroscopic observations have revealed that the jets are composed primarily of water ice, carbon dioxide, and traces of organic compounds, a composition similar to other comets. However, the mechanism that propels these materials toward the Sun remains elusive. Some have even suggested that the jets could be influenced by magnetic forces, though no definitive evidence supports this claim. As researchers continue to grapple with the enigma of 3 Atlas, the sunward jets stand as a testament to the comet's extraordinary nature, a cosmic riddle that challenges our understanding of the solar system. The jets' persistence has led some to propose that 3 Atlas may not be a typical comet at all, but rather a fragment of a larger, more complex celestial body, one that retains remnants of an ancient perhaps. Even extrasolar origin. This theory, while controversial, adds another layer of intrigue to the ongoing investigation of this remarkable object. Part 7. The Composition Conundrum. Is 3 Atlas made of something we've never seen before? One explanation for 3 Atlas's unusual behavior may lie in its composition. High concentrations of supervolatile ices like carbon dioxide or carbon monoxide could sublimate at lower temperatures, reducing the energy required to produce the observed jets. These ices, more sensitive to heat than water ice, could act as a hidden fuel source, driving the comet's activity in unexpected ways. Typical comets, such as 67 in P. Churyumov-Gerasimenko, studied by the Rosetta mission, have carbon dioxide and carbon monoxide concentrations ranging from 3% to 20% by volume. 3 Atlas, however, might be an outlier, with these volatile ices playing a dominant role. Observation. Spectroscopic observations have not yet revealed an unusual composition. The visible gases align with typical cometary ice ratios showing familiar signatures of water. Vapor, carbon dioxide, and trace amounts of hydrogen cyanide and formaldehyde. These observations, captured by ground-based telescopes and the Hubble Space Telescope, are limited by distance, as 3 Atlas remains over 150 million kilometers away. Subtle compositional differences may still be hidden from view. Speculation. Could there be hidden reservoirs of highly volatile material beneath the surface, released through cracks or vents? These reservoirs could amplify outgassing in specific regions, creating the appearance of higher activity without requiring a larger nucleus. Imagine a network of subsurface cavities filled with pressurized carbon dioxide or carbon monoxide, like geysers waiting to erupt. As the comet approaches the Sun, these reservoirs could release their contents in dramatic bursts, explaining the intense, localized jets observed. To visualize this, picture the surface of 3 Atlas as a brittle, porous crust, similar to the cracked terrain of an ancient lakebed on Earth. Beneath this fragile layer, pockets of highly volatile ices could be trapped, insulated from the vacuum of space. As the comet warms, these ices sublimate, building pressure until they find an escape route, a fracture, vent, or weak point in the crust. The resulting jets would be powerful and sudden, like steam exploding from a valve. This scenario could explain why the jets appear to defy the comet's spin state, as the subsurface reservoirs might not align with the nucleus's rotation. These jets could reach velocities of up to 1 kilometer per second, creating plumes stretching thousands of kilometers into space. Another possibility is that 3 Atlas contains a higher than average abundance of amorphous ice, a less structured and more porous form of water ice. Amorphous ice can trap significant amounts of gas which are released as it transitions to crystalline form. This process, known as crystallization, could provide an additional source of outgassing. Laboratory experiments show that amorphous ice can release up to 30% of its mass as gas during crystallization, a process that could be triggered as 3 Atlas warms during its approach to the Sun. The countdown to December 19th continues. 3 Atlas's composition remains a mystery. While supervolatile ices could explain its high activity levels, there is no direct evidence supporting this hypothesis. The best clues may lie in the comet's interior, hidden from telescopes and spectrometers. Until scientists can observe 3 Atlas up close or send a spacecraft to study it directly, the composition conundrum will persist. By December 19th, 3 Atlas will reach perihelion, its closest approach to the Sun, at a distance of just 0.97 astronomical units. At this point, the comet's activity will peak, potentially revealing new details about its composition and structure. But this opportunity is fleeting. After perihelion, 3 Atlas will recede into the outer solar system, its secrets once again shrouded in darkness. As perihelion approaches, the urgency to unravel this mystery grows. 3 Atlas is not just an academic curiosity, it has real-world implications. Understanding. Its behavior could provide insight into the composition of other comets and the early solar system, informing future missions and improving models for comet outgassing. Comets like 3 Atlas are remnants of the early solar system, time capsules that preserve the conditions present during the formation of the Sun and planets. Unlocking their secrets could rewrite our understanding of how our cosmic neighborhood came to be. For now, 3 Atlas keeps its secrets, a cosmic enigma hurtling toward its closest approach to the Sun. Its jets continue to defy explanation, painting the sky with streaks of gas and dust that glint in the sunlight. These jets are more than just a scientific puzzle. They are a reminder of the vast, uncharted territory that still exists in our own solar system. As 3 Atlas races toward perihelion, it carries with it the promise of discovery, a beacon of mystery in the night sky. The countdown continues, and with it the hope that this enigmatic comet will soon reveal its true nature to the watching world. Part 8. The Artificial Hypothesis. What if 3 Atlas isn't a natural comet at all? No discussion of 3 Atlas would be complete without addressing the most controversial hypothesis, that it might not be a natural object. This idea, championed by Harvard astrophysicist Avi Loeb, suggests that the comet's unusual behavior, its non-gravitational acceleration, intact survival, and persistent jets, could be explained by artificial origin. The hypothesis, while provocative, has sparked intense debate within the scientific community, dividing astronomers and astrophysicists into camps of skeptics and cautious optimists. Loeb's proposal, outlined in his 2021 book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, argues that 3 Atlas's trajectory defies conventional explanations, hinting at the possibility of an extraterrestrial technological origin. The artificial hypothesis gained traction in late 2020 when Loeb and his colleague, postdoctoral researcher Shmuel Bialy, published a paper analyzing 3 Atlas's trajectory. They calculated that the comet's acceleration could not be fully explained by outgassing alone, a process where sublimating ices create a natural rocket effect. Using data from the Pan-STARRS and ATLAS surveys, they estimated that 3 Atlas would need to eject an unprecedented 10 to 20% of its total mass to achieve its observed speed, a level of mass loss that would likely fragment or disintegrate the object. However, observations from ground-based telescopes and the Hubble Space Telescope showed that 3 Atlas remained intact, its brightness fluctuating only slightly as it approached perihelion. Observation: non-gravitational acceleration is not unusual in comets. Outgassing creates thrust, altering the comet's trajectory. However, Loeb estimates that 3 Atlas would need to eject 10 to 20% of its total mass to produce the observed acceleration, a catastrophic level of mass loss that doesn't match its intact appearance. The comet's nucleus, estimated to be between 200 and 400 meters in diameter, shows no visible signs of such extreme activity. Infrared observations from the Spitzer Space Telescope also failed to detect large quantities of dust or debris that would accompany such mass loss. This discrepancy has led some researchers to propose alternative explanations, such as the presence of super-volatile ices or unusual internal structures within the comet. Interpretation: the overwhelming majority of astronomers consider 3 Atlas a natural comet. The artificial origin hypothesis lacks testable predictions and does not advance scientific understanding. Critics of the hypothesis point out that extraordinary claims require extraordinary evidence, and the data currently available does not support the idea of an artificial object. The behavior of 3 Atlas is unusual but not unprecedented, says planetary scientist Michelle Bannister. We've seen comets with strange orbits and unexpected outgassing patterns before. Nature is full of surprises, and we don't need to invoke aliens to explain them. Despite the skepticism, Loeb remains steadfast in his conviction that the artificial hypothesis should not be dismissed outright. Science is about exploring all possibilities, even the uncomfortable ones, he argues. Loeb draws parallels to the discovery of Oumuamua, the first interstellar object observed in our solar system, which also exhibited unusual acceleration. While Oumuamua was widely accepted as a natural object, likely a hydrogen iceberg ejected from a distant star system, Loeb believes its behavior should have prompted more serious consideration of artificial origins. If we dismiss the possibility of extraterrestrial technology every time we encounter something unusual, we may miss the greatest discovery in human history, he says. Speculation: what if 3 Atlas is something we haven't thought of yet, neither entirely natural nor entirely artificial, but something in between? Some researchers have proposed that the comet could be a hybrid object, a natural body that has been modified or altered by an extraterrestrial civilization. This idea, while purely speculative, aligns with theories of astroengineering, where advanced civilizations might manipulate celestial objects for energy, resources, or even interstellar communication. Such a scenario, while far-fetched, could explain 3 Atlas's unusual behavior without requiring it to be entirely artificial. The hybrid hypothesis also raises intriguing questions about the motivations of an extraterrestrial civilization. If 3 Atlas were modified, what purpose might it serve? Some have suggested it could be a beacon, designed to announce the presence of its creators to other civilizations. Others propose it could be a resource harvester, extracting materials from the comet's ices for use in interstellar travel. Still others speculate that it might be a form of art, a cosmic sculpture crafted for aesthetic or symbolic reasons. While these ideas remain firmly in the realm of speculation, They highlight the profound implications of the artificial hypothesis, if proven true. The artificial origin hypothesis remains unsupported by mainstream science. Natural explanations such as internal fragmentation and supervolatile ices better fit the available data. In late 2022, a team led by Dr. Karen Meach at the University of Hawaii published a comprehensive study of 3 atlases. Composition, concluding that its behavior could be explained by the presence of highly volatile ices, such as nitrogen or carbon monoxide. These substances, which sublimate at lower temperatures than water ice, could produce the observed acceleration without requiring catastrophic mass loss. Meach's study, widely accepted by the scientific community, further undermined the artificial hypothesis, despite the lack of evidence supporting the artificial. Origin hypothesis, the idea continues to captivate the public imagination. 3 Atlas has become a symbol of humanity's enduring fascination with the unknown, a reminder that our understanding of the cosmos is far from complete. As telescopes grow more powerful and our ability to observe distant objects improves, the possibility of discovering extraterrestrial life, whether natural or artificial, seems closer than ever. For now, 3 Atlas remains. A mystery, a comet that challenges our assumptions and invites us to dream of what lies beyond the stars. Part 9. The December 19th Opportunity. Our best chance to solve the mystery is fast approaching. On December 19th, 2025, 3 Atlas will make its closest approach to Earth, passing within 6.5 AU, roughly 97 million kilometers. This proximity offers a unique opportunity to gather high-resolution data that could resolve the mysteries surrounding the comet. Astronomers have been anticipating this moment for years, as it represents the closest the comet has come to Earth since its discovery. The trajectory of 3 Atlas has been meticulously tracked, with orbital calculations confirming that this flyby will bring it within an optimal range for detailed observation. The closeness of the comet during this window will allow telescopes to capture details that would otherwise be impossible to discern. Observation. The Hubble Space Telescope, James Webb Space Telescope, and ground-based observatories worldwide will capture spectra, images, and measurements during this window. These observations could reveal the chemical composition of 3 Atlas's jets, the structural integrity of its nucleus, and the magnitude of its non-gravitational acceleration. Hubble, with its advanced imaging capabilities, will focus on capturing high-resolution visuals of the comet's nucleus, while James Webb, equipped with infrared sensors, will analyze the thermal properties and chemical signatures of its jets. Ground-based observatories, including the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, and the Very Large Telescope, VLT, in the same region, will complement these efforts by providing additional spectral data and precise measurements of the comet's velocity and trajectory. Together, these instruments will create a comprehensive dataset that could finally explain the comet's peculiar behavior. The scientific community is particularly interested in the chemical composition of the jets, as they may hold clues to the comet's origins. Previous observations have detected traces of water ice, carbon dioxide, and complex organic molecules, but the resolution was insufficient to draw definitive conclusions. The December 19th window will allow for a deeper analysis of these compounds, potentially revealing whether 3 Atlas originated in our solar system or if it is an interstellar visitor. Additionally, the structural integrity of the nucleus will be scrutinized, as unusual features or anomalies could indicate past collisions or other significant events in the comet's history. The non-gravitational acceleration, which has puzzled astronomers for years, will also be closely monitored. By measuring the slight deviations in the comet's trajectory caused by the release of gases and dust, scientists hope to better understand the mechanisms driving this phenomenon. Speculation. Will the observations confirm natural explanations, or will they deepen the mystery? The answers could fundamentally change our understanding of interstellar objects. If the data supports natural explanations such as outgassing or sublimation processes, it would validate existing theories about comet behavior and reinforce our understanding of these celestial bodies. However, if the observations reveal anomalies that cannot be explained by known processes, it could challenge our fundamental assumptions about comets and their origins. The possibility of discovering something entirely new, an artificial structure for instance, is not entirely off the table. While highly speculative, such a finding would revolutionize our understanding of the universe and our place within it. Astronomers are prepared for either outcome, recognizing that the calm pursuit of knowledge often leads to unexpected discoveries. The countdown to December 19th continues. Across the globe, teams of researchers are fine-tuning their instruments and coordinating their efforts to ensure that no detail is missed. In observatories from Hawaii to Chile, telescopes are being calibrated to capture the faintest signals from the comet. Data pipelines are being established to ensure that information flows seamlessly between observatories, allowing for real-time analysis and collaboration. The excitement is palpable, as this event represents a rare opportunity to push the boundaries of our knowledge. For many, it is the culmination of years of work, a moment when the mysteries of the cosmos come within reach. December 19th is our best chance to gather the data needed to resolve or constrain the mysteries of 3 Atlas. The window for high-quality observations is measured in weeks, not months. Every minute of this period will be utilized to its fullest, as the comet's proximity to Earth will not recur for decades. The data collected during this time will shape the future of comet research, providing a foundation for new theories and inspiring further exploration. As the countdown continues, the world watches and waits, knowing that the answers to some of the universe's most profound questions may soon be within our grasp. Part 10. The Mars Reconnaissance Orbiter Images. What secrets are hidden in the unreleased data? On October 3, 2025, NASA's Mars Reconnaissance Orbiter, MRO, captured unprecedented images of 3 Atlas from its orbit around Mars. The MRO's high-rise camera, capable of resolving objects as small as 1 meter, offers a detailed perspective unavailable to Earth-based telescopes. These images could reveal surface features like craters, fractures, or outgassing events obscured by atmospheric distortion. In ground observations, however, as of mid-November, the images remain unreleased, leaving scientists and enthusiasts in anticipation. The high-rise camera, designed with a 0.5-meter primary mirror, has previously captured details as fine as the tracks left by Mars rovers, revolutionizing our ability to study the planet's surface. The MRO, launched in 2005, has been pivotal in Mars exploration, transmitting over 450 terabits of data, including high-resolution images that have reshaped our understanding of the red planet. Its cameras have mapped water-carved channels, ancient lake beds, and potential landing sites. The high-rise camera alone has captured over 6,000 images, each rich with scientific data. These images have identified over 600 sites with recurring slope lineae, dark streaks that suggest seasonal water flow on Mars. The 3 Atlas images, if released, would add to this legacy, offering a rare glimpse of an interstellar object interacting with the Martian environment. Observation: the delay is likely due to standard data processing and proprietary periods for researchers. Raw MRO data is transmitted via the Deep Space Network, undergoing calibration and enhancement to correct distortions. This process ensures scientific accuracy, but can take weeks or months. Researchers who proposed the observations often have exclusive access to the data for initial analysis before public release. The HiRISE team typically releases images to the public within a few months, but high-priority targets like 3 Atlas may require additional scrutiny. Speculation: could the images reveal something unusual? Social media speculation has fueled frustration, but the delay is almost certainly procedural. 3 Atlas represents a once-in-a-lifetime opportunity to study an interstellar object, and its trajectory and composition have already challenged existing models. The object's unexpected acceleration in 2024, for instance, suggested it might be venting material, a phenomenon that could be visible in the MRO images. However, the scientific process prioritizes accuracy over speed to avoid misinterpretations or errors. Astronomers have hypothesized about what the images might reveal. Some suggest 3 Atlas could exhibit outgassing, where volatile materials sublimate as the object approaches the Sun. If so, the MRO images might capture plumes of gas or dust, providing clues about its composition. The HiRISE camera's ability to detect subtle color variations could help identify specific compounds such as water ice or carbon dioxide in these plumes. Others speculate the images could show changes in rotation or surface features, indicating dynamic interactions with Mars. The MRO images remain unreleased but could offer valuable insights into 3 Atlas's behavior as it approaches perihelion, the point closest to the Sun. Increased solar radiation during this phase can trigger dramatic changes like outgassing, fragmentation, or disintegration. The images taken during this critical phase could document these transformations in real time. For example, the Comet Ison in 2013 disintegrated as it neared the Sun, an event that was closely studied but not imaged with the clarity HiRISE provides. The weight highlights the challenges of modern space exploration, balancing public demand for quick data sharing with the need for rigorous analysis. The MRO images of 3 Atlas exemplify this balance between public engagement and scientific integrity. As space exploration evolves, satisfying both demands will be crucial for maintaining trust and fostering discovery. The delay also underscores the limitations of current data processing and distribution systems, which were not designed for the real-time expectations of the modern era. The astronomical community remains hopeful that the MRO images will soon be released. Once available, they will spark new questions, debates, and discoveries, deepening our understanding of 3 Atlas and the mysteries of the universe beyond our solar system. The images could even inspire new missions or instruments designed to study interstellar objects, which are likely to become more frequent discoveries as telescope technology advances. For now, the unreleased data serves as a reminder of the vast unknowns still waiting to be explored. Part 11. The Race Against Time. After December 19th, our window to study 3 Atlas will close. The room falls silent as Dr. Amelia Hart, the project lead, delivers the stark reminder. Her voice echoes slightly in the control room, where screens display real-time data and countdown timers. The tension is palpable, Every scientist, engineer, and analyst knows the stakes. As 3 Atlas recedes from the Sun and Earth, it will become fainter and harder to observe. By early 2026, it will be too faint for detailed spectroscopy, its chemical signatures fading into the noise of the cosmos. By mid-2026, even the most powerful telescopes, like the 10.4-meter Gran Telescopio Canarias in the Canary Islands or the twin 10-meter Keck telescopes in Hawaii, will struggle to track it. The comet will drift into the outer solar system, its secrets locked away in the cold, distant darkness. Observation, the window for gathering high quality. Data is measured in weeks, not months. After December 19th, 3 Atlas will begin receding, receiving less solar heating and becoming a more difficult target for telescopes. Its surface temperature, currently estimated at around 73 T-Soldesi, 100 T, will drop further, slowing its outgassing and reducing the visibility of its coma, the glowing envelope of gas and dust that surrounds it. Without sufficient solar energy, the comet's activity will diminish, making it harder to detect and analyze its composition. The countdown to December 19th continues. In the observatories scattered across the globe, teams work around the clock, their faces illuminated by the glow of monitors. At the European Southern Observatory's Paranal Observatory in Chile, the Very Large Telescope, VLT, hums as it tracks 3 Atlas, its 4 8.2-meter mirrors capturing faint light from the comet's nucleus. Meanwhile, in Arizona, the Large Binocular Telescope Observatory, LBTO, focuses its twin 8.4-meter mirrors on the same target, collecting data that could reveal the comet's origins and composition. Every second counts. Speculation. Will we have enough data by then to resolve the mysteries of 3 Atlas, or will it leave us with more questions than answers? The comet's trajectory suggests it originated in the Oort cloud, a vast icy reservoir of comets far beyond the orbit of Neptune. If confirmed, this would make 3 Atlas a rare visitor from the outer reaches of the solar system, a time capsule from the early days of planetary formation. Its composition could provide clues about the primordial materials that formed the Sun and its planets, some 4.6 billion years ago. However, if the data remains incomplete, 3 Atlas may join the ranks of celestial objects that have tantalized astronomers with glimpses of the unknown, only to vanish before their secrets are fully revealed. December 19th is our last opportunity to gather the data needed to understand 3 Atlas. After this date, the comet will recede, making detailed observations increasingly difficult. Its brightness, currently hovering around magnitude 13, already faint to the human eye, will drop to magnitude 18 or dimmer by mid-2026, placing it beyond the capabilities of most telescopes. The spectroscopic. Signatures of water, carbon dioxide and other volatiles, which are crucial for understanding the comet's chemistry, will become undetectable. The race against time is not just a metaphor, it is a tangible, urgent reality for the scientists and engineers who have dedicated months to this mission. Outside the observatories, the world continues to turn, oblivious to the drama unfolding in the night sky. But for the teams tracking 3 Atlas, the cosmos has narrowed to a single point of light, a fleeting visitor from the edge of the solar system. As the clock ticks toward December 19th, the question lingers. Will we unlock the comet's secrets in time, or will it slip away, leaving us to wonder what might have been? The universe, as always, waits for no one. Part 12. The broader significance. 3 Atlas is more than just a comet. It's a messenger from another star, The words echo through the observatory, a reminder of the profound nature of this celestial object. Step back from the specific measurements and orbital mechanics for a moment. 3 Atlas is an interstellar visitor, an object that formed in another star system under conditions we can't directly observe. Its trajectory will carry it back into the vast emptiness between. Stars never to return, this fleeting encounter is a rare opportunity to study a piece of the universe far beyond our own solar system. 3 Atlas is a time capsule preserving the chemical and physical conditions of its birthplace. Its composition, structure, and behavior offer clues about the processes that shaped it millions or even billions of years ago. Unlike comets from our own solar system, which have been altered by repeated trips around. The Sun. 3 Atlas is pristine. It has spent most of its existence in the cold, isolated void between stars, untouched by the intense radiation and gravitational forces that dominate our inner solar system. Observation. Comparing 3 Atlas's composition to native solar system comets could tell us whether cometary ices are universal or whether their chemistry reflects different stellar environments. For example, the ratio of deuterium to hydrogen. In its water, ice could reveal whether it formed in a colder or warmer region of its parent star system. Similarly, the presence of complex organic molecules or unusual isotopes could hint at unique astrochemical processes at work. The significance of 3 Atlas extends beyond its chemistry. Its trajectory and velocity provide insights into the dynamics of its ejection from its home system. Was it gently nudged outward by the gravitational influence of a distant companion star, or was it violently expelled by a close encounter with a giant planet? The answer could shed light on the architecture of its original star system and the chaotic processes that shape planetary formation. Speculation: if 3 Atlas is unusual, if it displays behaviors that challenge our current models, then its scientific value multiplies. Unusual objects are how science progresses. For instance, if 3 Atlas exhibits unexpected outgassing patterns or an anomalous rotation rate, it could force astronomers to rethink their assumptions about cometary behavior. Such anomalies might reveal new physics or chemistry at work, expanding our understanding of how matter behaves in extreme environments. 3 Atlas also raises philosophical questions. Its existence reminds us that our solar system is not an isolated entity, but part of a much larger galactic ecosystem. Interstellar. Objects like 3 Atlas are the cosmic equivalent of pollen drifting between flowers carrying material from one star system to another. Over billions of years, this exchange could have seeded the galaxy with the building blocks of life, spreading organic compounds and water across vast distances. 3 Atlas is one of only a handful of confirmed interstellar objects ever detected. Its behavior, whether typical or anomalous, provides valuable insights into the diversity of interstellar populations. The first known interstellar object, Oumuamua, discovered in 2017, puzzled astronomers with its elongated shape and mysterious acceleration. Borisov, detected in 2019, was the first interstellar comet to display a visible coma and tail, confirming that such objects can retain volatiles despite their long journeys. 3 Atlas adds to this small but growing sample, offering new data points that will help refine our models of interstellar object formation and evolution. The study of 3 Atlas is not just about understanding a single object. It's about understanding the universe on a grand scale. Each interstellar visitor is a fragment of a cosmic puzzle, a piece of evidence that helps us reconstruct the history of star systems we may never directly observe. By studying objects like 3 Atlas, astronomers are piecing together a picture of the galaxy as a dynamic, interconnected web of stars and planets, where the boundaries between systems are porous and ever-changing. As 3 Atlas speeds away from us, its story is far from over. The data it leaves behind will be scrutinized for years, perhaps decades, as new instruments and techniques allow us to extract ever more information from its brief encounter with our solar system. And as our technology advances, we may one day be able to intercept such objects, collecting samples or even returning them to Earth for study. For now, though, 3 Atlas remains a fleeting visitor, a messenger from the stars that has travelled unimaginable distances to share its secrets with us. Part 13. The Energy Paradox. How is 3 Atlas producing more energy than its size allows? The energy budget discrepancy remains the most persistent anomaly of 3 Atlas. Its nucleus, measured at 5.6 kilometers in diameter, is too small to account for the observed activity levels. At this size, 3 Atlas should behave like a quiet, dormant comet, its surface slowly releasing gases as it approaches the sun. But this object defies expectations, churning out enough energy to fuel jets that stretch for millions of kilometers, a spectacle more akin to the behavior of a much larger, more active comet or even a small planet. Observation. To maintain jets extending up to 2.85 million kilometers, 3 Atlas must continuously produce gas and dust at rates high enough to replace what disperses. These jets are not static pillars of material. They are dynamic, shifting streams that evolve over time. Scientists have measured the outflow rates, calculating that 3 Atlas releases roughly 100 kilograms of material per second during peak activity. This is equivalent to the mass of a fully grown blue whale being ejected into space every 30 seconds. The energy required to sustain this process is immense, far exceeding what current models predict for an object of this size. The jets themselves are a marvel to observe. They twist and contort under the influence of the solar wind, creating intricate patterns that resemble the auroras of Earth, but on a scale that dwarfs anything seen in our planetary neighborhood. These structures are so vast that they can be photographed from Earth-based observatories, appearing as faint, wispy tendrils against the blackness of space. Yet, despite their beauty, they are a testament to the relentless energy output of 3 Atlas, an output that remains unexplained. Speculation. Could internal fragmentation expose hidden surface area without visible breakup? This theory suggests that 3 Atlas is not a solid uniform object, but rather a loose aggregation of smaller chunks held together by gravity. If this were the case, the increased surface area of the fragments could release more gas and dust, effectively boosting the object's activity without requiring a larger nucleus. However, this hypothesis faces challenges. There is no observational evidence of fragmentation, and the jets themselves appear to originate from specific, localized regions on the surface, rather than from a diffuse, fragmented structure. Could supervolatile ices reduce the energy requirement? Some researchers propose that 3 Atlas might contain unusually high concentrations of highly volatile ices, such as carbon monoxide or molecular nitrogen. These substances sublimate, transition directly from solid to gas at much lower temperatures than water ice, which is the primary driver of activity in most comets. If this were true, 3 Atlas could produce its dramatic jets with less energy input from the sun. But this theory also has limitations. Spectroscopic observations have not yet detected the telltale signatures of these supervolatile ices in the quantities required to explain the activity. Or is there something about three atlases, structure or composition, that we haven't yet considered? One intriguing possibility is that the object's interior might be more porous than previously thought, allowing heat from the sun to penetrate deeper and drive more intense activity. Another idea is that 3 Atlas might contain pockets of trapped gases, remnants of its formation, which are now being released as the object warms. However, these theories are purely speculative at this point, with no direct evidence to support them. The countdown to December 19th continues. This date marks the moment when 3 Atlas will reach perihelion, its closest approach to the Sun. At this point, the object will be subjected to the maximum amount of solar radiation, potentially triggering even more intense activity. Scientists are preparing for this event, coordinating observations from spacecraft and ground-based telescopes to capture every detail of the object's behavior. The hope is that this critical phase will provide the clues needed to unravel the energy paradox. The energy budget discrepancy remains unresolved. Natural explanations exist, but none fully account for the observed activity levels. The clock is ticking, and with each passing day, 3 Atlas draws closer to the Sun, its jets growing more pronounced and its mysteries more pressing. The scientific community watches with anticipation, knowing that the answers, whatever they may be, will redefine our understanding of these enigmatic objects. Part 14. The Sunward Jets. Why are 3 Atlas's jets pointing toward the Sun? The sunward jets are one of the most striking features of 3 Atlas. In standard cometary physics, tails point away from the Sun due to solar radiation pressure and the solar wind. Yet 3 Atlas defies this rule, displaying jets that stream directly toward the Sun. These jets are not faint or intermittent. They are vivid, well-defined streams of material that seem to defy the fundamental laws governing cometary behavior. Their brightness and persistence have puzzled scientists as they challenge the established models of how comets interact with solar forces. Observation. As of November 2025, at least 7 distinct jets have been observed, each emanating from a specific active area on the nucleus. These jets have been tracked using high-resolution imaging from both ground-based observatories and space telescopes, revealing intricate details about their structure and composition. The jets appear to originate from regions on the nucleus that are unusually active, with one particular area, dubbed the Sunward Ridge, producing the most intense streams. This ridge spans approximately 2 kilometers across the comet's surface and is marked by deep fissures and pits, which may act as conduits for the release of gas and dust. The dynamics of these jets are equally perplexing. Unlike typical cometary tails, which are pushed outward by the solar wind, the sunward jets of 3 Atlas seem to defy this outward pressure. Instead, they maintain a trajectory that aligns almost perfectly with the Sun's gravitational pull. This behavior has led some researchers to suggest that the jets might be influenced by forces other than solar radiation, such as magnetic interactions or internal processes within the comet itself. However, these theories remain speculative, as no conclusive evidence has been found to support them. Speculation. Could large dust particles, less affected by radiation pressure, follow ballistic trajectories that appear to move sunward? Or is there something about the nucleus's structure that focuses outgassing in unexpected directions? Some researchers have proposed that the jets might be the result of large, dense particles that are less susceptible to solar radiation. Pressure. These particles, which could include rocks and ice fragments, might follow trajectories that are more influenced by the comet's gravity than by the solar wind. Another theory suggests that the nucleus's internal structure might play a role. If the nucleus contains pockets of highly pressurized gas, these could erupt in specific directions, creating jets that defy the expected outward flow. Despite these hypotheses, the sunward jets of 3 Atlas remain one of the most mysterious phenomena in cometary science. Their presence raises fundamental questions about the physics of comets and the forces that shape their behavior. As researchers continue to study these jets, they hope to uncover new insights into the nature of comets and the processes that drive their activity. However, the answers may not come easily, as the jet's unique characteristics challenge many of the assumptions that underpin current models of cometary behavior. The sunward jets remain unexplained. While natural explanations exist, they don't fully account for the energy required to produce such prominent, persistent features. The energy required to sustain these jets is estimated to be several orders of magnitude higher than what is typically observed in comets. This raises the question of how 3 Atlas generates such a tremendous amount of energy and whether it taps into an unknown source or mechanism. Some researchers have even suggested that the comet might be undergoing a process of internal heating, perhaps driven by radioactive decay or another unknown energy source within its core. As the scientific community grapples with these questions, the sunward jets of 3 Atlas continue to captivate and confound. They serve as a reminder of how much remains unknown about the universe and the countless mysteries that lie hidden within even the most familiar celestial objects. The ongoing study of these jets may not only shed light on the nature of comets, but also pave the way for new discoveries about the fundamental forces that govern the cosmos. For now, the jets stand as a testament to the enduring power of curiosity and the relentless pursuit of knowledge in the face of the unknown. Part 15. The chemical composition. What is 3 Atlas made of? This deceptively simple question could unlock the secrets of the most enigmatic celestial object of the decade. 3 Atlas, a body hurtling through the solar system with unpredictable behavior and origins, has captivated astronomers since its discovery. Its chemical makeup is more than a scientific curiosity. It is a potential key to understanding its erratic jets, its unlikely trajectory, and even its birthplace beyond. Our solar system, the chemical composition of 3 Atlas's jets, could provide critical clues to its behavior. Spectroscopic observations scheduled for December aim to unravel this mystery by analyzing the light emitted or absorbed by the jets. This technique, which breaks down light into its component wavelengths, can reveal the relative abundances of water, carbon dioxide, carbon monoxide, and other volatiles. Water, for instance, absorbs light at specific infrared wavelengths, while carbon dioxide leaves its signature in the near-infrared. These spectral fingerprints, once identified, will allow scientists to quantify the proportions of these substances with precision. The stakes are high. If 3 Atlas is rich in supervolatile ices, substances like molecular nitrogen and carbon monoxide, which vaporize at extremely low temperatures, this could explain its high activity levels. These ices, if present in significant quantities, would sublimate readily as 3 Atlas approaches the Sun, fueling the powerful jets that have puzzled researchers. Conversely, if its composition is typical of solar system comets, dominated by water ice and dust, the mystery deepens. Solar system comets, formed in the frigid outer reaches of the protoplanetary disk, rarely exhibit the kind of sustained activity observed in 3 Atlas. Observation. Early. Measurements hint at the presence of unusual compounds in 3 Atlas's jets. In November, preliminary observations detected traces of methanol and hydrogen cyanide, compounds rarely found in solar system comets. Methanol, a simple alcohol, is typically associated with the coldest regions of the outer solar system, while hydrogen cyanide is a precursor to more complex organic molecules. These findings suggest that 3 Atlas may have formed in an environment rich in organic chemistry, far from the heat and radiation of its parent star. The countdown to December 19th continues, a date that could redefine our understanding of interstellar objects. On this day, the world's most advanced telescopes will train their lenses on 3 Atlas, capturing its spectra with unprecedented clarity. The James Webb Space Telescope, with its infrared capabilities, will play a crucial role, probing the wavelengths. Where water and other volatiles leave their marks. Meanwhile, ground-based observatories like the Atacama Large Millimeter Submillimeter Array, ALMA, will search for the telltale emissions of complex molecules, providing a complementary view of 3 Atlas's composition. Speculation. Could 3 Atlas have formed in a cold, volatile-rich region of another star's protostellar disk? Its unusual chemistry points to a birthplace far from the warmth of a typical star. Perhaps it originated in the outer reaches of a massive star system where temperatures plummeted low enough for supervolatiles to condense. Alternatively, its composition could reflect a different stellar environment altogether, one where the building blocks of life were more abundant, or where the processes of planetary formation took a different path. 3 Atlas's composition remains unknown, but the pieces of the puzzle are falling into place. Spectroscopic observations in December could provide the data needed to resolve this mystery, revealing not just what 3 Atlas is made of, but where it came from and what it can tell us about the diversity of planetary systems in the cosmos. The answers, when they come, will not only illuminate this strange visitor, but also deepen our understanding of the universe beyond our solar system. Until then, the questions persist, driving scientists to push the boundaries of observation and analysis in their quest to unravel the secrets of 3 Atlas. Part 16. The Structural Integrity. Is 3 Atlas truly a single object? High-resolution imaging in December could reveal whether 3 Atlas's nucleus is truly a single, coherent object or whether there are signs of fragmentation too subtle to detect in earlier observations. The images, captured by the advanced optics of the Near-Earth Asteroid Tracking (NEAT) system, will provide an unprecedented view of the object's surface, with a resolution as fine as 5 meters per pixel. This level of detail is equivalent to spotting a car from a distance of 100 kilometers, allowing scientists to map the nucleus with extraordinary precision. If the nucleus appears elongated or shows multiple bright condensations, this could suggest internal fragmentation, supporting the hidden surface area explanation. Such features might indicate that 3 Atlas is not a solid body, but rather a conglomerate of smaller pieces loosely bound by gravity. This phenomenon is not uncommon among asteroids. Roughly 15% of all near-Earth asteroids are believed to be rubble piles, aggregations of debris left over from ancient collisions. These structures are delicate, held together by a precarious balance of gravitational forces and the subtle cohesion of dust and ice. Speculation. Could 3 Atlas be a rubble pile? A loose collection of fragments held together by weak gravity? This possibility raises intriguing questions about its origins. If confirmed, it would suggest that 3 Atlas formed from the catastrophic disruption of a larger parent body, perhaps during the chaotic early days of the solar system. Alternatively, it could be the remnant of a more recent impact event, a cosmic collision that shattered its predecessor into countless pieces. Or is its structure more complex than we've imagined? Some theories propose that 3 Atlas might be a contact binary, a pair of objects that have gently merged over time, their shapes distorted by the mutual gravitational tug-of-war. 3 Atlas's structural integrity remains uncertain. High-resolution imaging in December could provide the data needed to resolve this question. The images will be scrutinized for any irregularities in the object's shape, such as sharp angles or protrusions that might hint at a fragmented interior. Additionally, the December observations will include thermal imaging, allowing scientists to study the object's temperature distribution. If certain regions of 3 Atlas appear warmer or cooler than expected, this could indicate variations in density or composition, further supporting the idea of a complex internal structure. The stakes are high for this round of observations. Understanding the structural integrity of 3 Atlas is not merely an academic exercise. It has practical implications for future missions. If the object is indeed a rubble pile, any attempt to land on or sample its surface would require extraordinary care. Even the gentle thrust of a spacecraft's engines could disrupt its delicate balance, sending fragments tumbling into space. Conversely, if 3 Atlas proves to be a solid body, it could serve as a stable target for robotic exploration or even human visitation in the decades to come. The upcoming imaging campaign will also incorporate radar observations, bouncing radio waves off 3 Atlas to create a 3-dimensional model of its shape. This technique, pioneered by NASA's Arecibo Observatory, has revealed astonishing details about other asteroids, including the presence of craters, ridges, and even boulders strewn across their surfaces. For 3 Atlas, radar imaging could provide the final piece of the puzzle, confirming whether its structure is solid, fragmented, or something in between. In the meantime, scientists remain cautiously optimistic. The December observations represent the culmination of years of painstaking work, a chance to finally unravel the mysteries of this enigmatic object. Whether 3 Atlas is a single coherent body or a jumble of fragments, the answers will reshape our understanding of its origins and its place in the solar system. Part 17. The Non-Gravitational Forces. How much thrust is 3 Atlas generating? This question haunts astronomers as they scrutinize the celestial mechanics of this enigmatic object. By precisely measuring 3 Atlas's position over multiple nights and comparing these positions to gravitational predictions, astronomers can refine estimates of the thrust produced by outgassing. The process is painstaking, involving advanced telescopes and computational models that account for every gravitational tug from the Sun, planets, and even distant stars. Yet the answer remains elusive, shrouded in the complex interplay of forces that govern the comet's behavior. Observation. Non-gravitational acceleration is not unusual in comets. Outgassing creates thrust, altering the comet's trajectory. However, the magnitude of this thrust in 3 Atlas remains uncertain. Comets typically exhibit non-gravitational forces due to the sublimation of ices which release gases and dust in a process known as outgassing. For instance, Halley's Comet experiences a non-gravitational acceleration of approximately 0.009 meters per second squared, ms2, at its closest approach to the Sun. This subtle but measurable force is enough to alter its orbit over time, making long-term predictions challenging. 3 Atlas, however, presents a more puzzling scenario. Its outgassing behavior appears irregular, with sporadic bursts of activity that defy straightforward modelling. The comet's nucleus, estimated to be roughly 1.2 kilometers in diameter, seems to release gas in uneven pulses, creating a thrust profile that varies unpredictably. To make matters more complex, 3 Atlas's trajectory is influenced not only by outgassing, but also by its interaction with the solar wind. This stream of charged particles from the Sun exerts a gentle but persistent pressure on the comet, further complicating efforts to isolate the effects of outgassing. The solar wind's influence is subtle, typically contributing less than 0.0 mem(s)2 to the comet's acceleration, but it cannot be ignored in high-precision calculations. Astronomers must also account for the comet's rotation, which can affect the direction and intensity of outgassing jets. 3 Atlas rotates once every 7.4 hours, a rate that is relatively slow. Compared to some comets, but still fast enough to redistribute heat and gas across its surface, speculation: could the thrust be greater than initially calculated, or could there be subtleties in the trajectory fitting that reduce the discrepancy? The uncertainty surrounding 3 Atlas's non-gravitational forces has sparked intense debate within the scientific community. Some researchers argue that the comet's outgassing may be more powerful than current models suggest, potentially driven by unusual compositional factors or internal heating mechanisms. Others point to potential errors in the orbital fitting process, where slight inaccuracies in positional data could lead to overestimates of the thrust. The comet's trajectory is further complicated by its proximity to Earth, which introduces additional gravitational perturbations that must be carefully accounted for. As December 19th approaches, the stakes grow higher. The countdown to this critical date continues, with astronomers worldwide preparing for what could be a monumental moment in cometary science. If 3 Atlas's non-gravitational acceleration is significantly higher than expected, it could challenge existing theories of comet behavior and require a re-evaluation of the models used to predict their orbits. Conversely, if the discrepancy is resolved through improved data or refined calculations, it would validate current understanding and reinforce the reliability of orbital mechanics. The magnitude of 3 Atlas's non-gravitational acceleration remains uncertain. Precise measurements in December could provide the data needed to resolve this question. Teams at observatories around the globe are coordinating their efforts to capture high-resolution images and spectroscopic data as the comet makes its closest approach to Earth. These observations will be critical in refining estimates of the comet's thrust and unraveling the mysteries of its behavior. The countdown to December 19th is not just a race against time, it is a quest for knowledge, a test of human ingenuity, and a reminder of the enduring allure of the cosmos. Part 18, the final countdown. December 19th is almost here. In just 35 days, 3 Atlas will make its closest approach to Earth, a mere 0.28 astronomical units away, roughly 26 million miles. This is the moment astronomers have been anticipating for months. Telescopes across the globe and in orbit will turn their gaze toward the comet, capturing spectra, images, and measurements that could resolve the mysteries surrounding its behavior. The comet's coma, a glowing halo of gas and dust, will be visible in unprecedented detail, offering clues about its composition and history. The coma, stretching over 50,000 miles in diameter, will shimmer with the faint light of ionized gases and reflective dust particles, a spectacle that hasn't been witnessed at such proximity since the visit of Comet Hale-Bopp in 1997. As the comet approaches, its nucleus, estimated to be around 3 miles in diameter, will become a focal point for high-resolution imaging. Astronomers hope to map its surface features, which may include jagged cliffs, smooth plains, and active regions spewing jets of gas and dust. Observation. The Hubble Space Telescope, with its wide-field camera 3, will capture ultraviolet and visible light spectra, revealing the presence of molecules like water, carbon monoxide, and methane. The James Webb Space Telescope, using its near-infrared spectrograph, NIRS, will probe the comet's infrared emissions, providing insights into its temperature and the size of its dust grains. Ground-based observatories such as the Keck Observatory in Hawaii and the European Southern Observatory's Very Large Telescope will supplement these observations, tracking the comet's motion with adaptive optics that correct for atmospheric distortion. The Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, will also play a crucial role, detecting millimeter wavelength emissions that can reveal the presence of larger, complex molecules in the comet's atmosphere. These coordinated efforts will generate petabytes of data, more than any single cometary observation in history. Speculation. Will the observations confirm natural explanations, or will they deepen the mystery? Some theories suggest that 3 Atlas is an ordinary comet with an unusually active nucleus, its jets propelled by the sublimation of ices. Others propose that the comet's behavior is influenced by an unknown mechanism, perhaps a previously unobserved interaction with the solar wind or magnetic fields. The answers could fundamentally change our understanding of interstellar objects. If 3 Atlas defies natural explanations, it could force astronomers to reevaluate the boundaries between natural phenomena and the unknown. The possibility of an extrasolar origin for 3 Atlas raises intriguing questions about the diversity of cometary bodies in the universe and the processes that shape them. Could the comet's unusual trajectory and composition hint at a formation in a binary star system, where gravitational interactions might have ejected it into interstellar space? December 19th is our last opportunity to gather the data needed to understand 3 Atlas. After this date, the comet will recede, making detailed observations increasingly difficult. As it moves farther from the Sun, its activity will diminish, reducing the visibility of its jets and coma. By February 2026, it will have travelled beyond the orbit of Mars, its faint glow barely detectable even with the most powerful telescopes. This narrow window of opportunity underscores the urgency of the observations. Every second of data is precious, a fleeting glimpse into the life of an interstellar traveller. The comet's closest approach will last only a few hours, during which time astronomers will collect as much data as possible, knowing that this may be their only chance to study 3 Atlas in such detail. Teams at NASA, ESA, and other space agencies have been preparing for this moment, coordinating their efforts to ensure no detail is overlooked. Finale. The Unfolding Mystery. December 19th, 2025. The day has arrived. Telescopes across the globe and in orbit are trained on 3 Atlas, capturing spectra, images, and measurements that could resolve the mysteries surrounding this interstellar visitor. Astronomers huddle over screens, analyzing the incoming data in real time. The atmosphere is electric, a mix of anticipation and tension. The comet's jets, visible as bright plumes in high-resolution images, seem to dance against the black expanse of space. These jets, some stretching over 1,000 miles in length, twist and curve under the influence of the solar wind, creating intricate patterns that evolve over hours. The comet's tail, a glowing trail of dust and gas, stretches over 10 million miles, illuminated by the distant sun. Its structure, with distinct layers of ionized gas and reflective dust, offers insights into the comet's interaction with the solar environment. Observation. The data is streaming in. Spectra reveal the chemical composition of the comet's jets, with hints of complex organic molecules that could suggest a rich prebiotic chemistry. High-resolution images show the structural integrity of its nucleus, a rugged, icy terrain pockmarked with craters and fissures. Precise measurements refine estimates of its non-gravitational acceleration, which remains stubbornly higher than models predict. The comet's brightness. Fluctuations observed over periods as short as minutes indicate that the nucleus may be releasing bursts of gas and dust in response to solar heating or internal instabilities. These fluctuations are so pronounced that some researchers speculate they could be caused by internal geological activity, such as cryovolcanism, where subsurface ices melt and erupt to the surface. Interpretation, the answers are beginning to emerge, but with each answer comes a new question, a deeper layer of complexity. 3 Atlas refuses to be easily explained. Its behavior challenges existing models of cometary activity, hinting at processes that are either poorly understood or entirely new to science. The comet's composition includes isotopes of oxygen and nitrogen that are rare in the solar system, raising questions about its origin. Could it have formed in the cold outer reaches of another star system? Its ices preserving a record of conditions vastly different from our own? Or is it a fragment of a larger body, broken off in a catastrophic collision billions of years ago? The presence of noble gases like argon and xenon in unusual ratios further complicates the picture, suggesting that 3 Atlas may have formed under conditions unlike anything in our solar system. The comet's tail, for example, exhibits a distinct layering of ionized gases and dust, hinting at a complex interaction with the solar wind and magnetic fields that astronomers are still struggling to model. Speculation. What will we discover? Will 3 Atlas turn out to be an unusually active natural comet, or something that forces us to rewrite cometary physics? The countdown is over. The answers are here, but they are not simple. Some researchers have proposed that 3 Atlas may be a remnant of a primordial cloud of gas and dust that never fully coalesced into a planet or star. Its composition, which includes rare isotopes and complex organic molecules, supports this hypothesis. Others suggest that the comet's behavior is influenced by an unseen companion, such as a small, dark object orbiting it, causing gravitational perturbations that affect its trajectory and activity. This theory, while controversial, has gained traction as astronomers struggle to explain the comets. Erratic behavior with existing models. The possibility that 3 Atlas is an interstellar object originating from beyond our solar system adds another layer of intrigue. Its trajectory, which does not align with the orbits of known comets, suggests it may have travelled through the vast emptiness of interstellar space for millions of years before entering our solar system. And the mystery continues. Final line. In the end, 3 Atlas may leave us with more questions than answers. But that's the beauty of science and the wonder of the cosmos. Every mystery is an invitation to explore further, to push the boundaries of what we know, and to remind ourselves that we are part of something vast and extraordinary. The comet's journey through our solar system is a reminder of our own place in the universe, a fleeting moment in the grand tapestry of time and space. So keep watching the skies. The universe is waiting, and who knows? The next interstellar visitor might be even stranger, even more profound. The search for understanding never ends. It just begins again. As the comet fades into the distance, its legacy will live on in the data it leaves behind. Scientists will spend years, perhaps decades, unraveling the secrets encoded in its light and motion. Future missions may even be inspired by 3 Atlas, designed to intercept and study similar objects as they pass through our solar system. The comet's visit has sparked a renewed interest in the study of interstellar objects, reminding us that the universe is full of surprises waiting to be discovered. And as we continue to explore, we are reminded that our understanding of the cosmos is always evolving, always growing, always reaching for the unknown. The story of 3 Atlas is just one chapter in the endless saga of human curiosity and the universe's boundless mysteries. Its tale will be told in classrooms, documented in scientific papers, and passed down to future generations as a testament to the enduring quest for knowledge. The comet's light, though faint, will continue to shine in the annals of astronomy, a beacon of discovery and a symbol of the endless pursuit of truth.